Okay, so to begin with, what we're going to look at is Zeno's paradox on 2.2, and I'm actually going to let you watch a little short video that's on YouTube because this is a good way to explain Zeno's paradox, and calculus really is what solves the dilemma. So I'm going to open this link, let you watch. This is a real good short video that'll show Zeno's paradox.
This is Zeno of Elea, an ancient Greek philosopher famous for inventing a number of paradoxes, arguments that seem logical but whose conclusion is absurd or contradictory. For more than 2,000 years, Zeno's mind-bending riddles have inspired mathematicians and philosophers to better understand the nature of infinity. One of the best known of Zeno's problems is called the dichotomy paradox, which means the paradox of cutting in two in ancient Greek. It goes something like this. After a long day of sitting around thinking, Zeno decides to walk from his house to the park. The fresh air clears his mind and helps him think better. In order to get to the park, he first has to get halfway to the park. This portion of his journey takes some finite amount of time. Once he gets to the halfway point, he needs to walk half the remaining distance. Again, this takes a finite amount of time. Once he gets there, he still needs to walk half the distance that's left, which takes another finite amount of time. This happens again and again and again. You can see that we can keep going like this forever, dividing whatever distance is left into smaller and smaller pieces, each of which takes some finite time to traverse. So, how long does it take Zeno to get to the park? Well, to find out, we need to add the times of each of the pieces of the journey. The problem is, there are infinitely many of these finite-sized pieces. So, shouldn't the total time be infinity? This argument, by the way, is completely general. It says that travelling from any location to any other location should take an infinite amount of time. In other words, it says that all motion is impossible. This conclusion is clearly absurd, but where's the flaw in the logic? To resolve the paradox, it helps to turn the story into a math problem. Let's suppose that Zeno's house is 1 mile from the park, and that Zeno walks at 1 mile per hour. Common sense tells us that the time for the journey should be 1 hour. But let's look at things from Zeno's point of view and divide up the journey into pieces. The first half of the journey takes half an hour. The next part takes quarter of an hour. The third part takes an eighth of an hour, and so on. Summing up all these times, we get a series that looks like this. Now, Zeno might say, since there are infinitely many terms on the right-hand side of the equation, and each individual term is finite, the sum should equal infinity, right? This is the problem with Zeno's argument. As mathematicians have since realized, it is possible to add up infinitely many finite-sized terms and still get a finite answer. How, you ask? Well, let's think of it this way. Let's start with a square that has area 1 unit. Now let's chop the square in half, and then chop the remaining half in half, and so on. While we're doing this, let's keep track of the areas of the pieces. The first slice makes 2 parts, each with an area of 1/2. The next slice divides one of those halves in half, and so on. But no matter how many times we slice up the boxes, the total area is still the sum of the areas of all the pieces. Now you can see why we chose this particular way of cutting up the square. We've obtained the same infinite series as we had for the time of Zeno's journey. As we construct more and more blue pieces, to use the math jargon, as we take the limit as n tends to infinity, the entire square becomes covered with blue. But the area of the square is just 1 unit, and so the infinite sum must equal 1. Going back to Zeno's journey, we can now see how the paradox is resolved. Not only does the infinite series sum to a finite answer, but that finite answer is the same one that common sense tells us is true. Zeno's journey takes 1 hour.
Okay, so that's kind of an interesting thing to look at for a beginning calculus student because you'll eventually learn about infinite series. So it seemed in his time that it was a paradox, but it's not a paradox. And this is kind of helps students understand the idea of what's going on a limit. Okay, so what I'm going to kind of look at here is doing some more things with our calculator to kind of establish this idea of a limit. And to begin with, on this example, what I'm going to do is we're going to graph this linear function. Now, a couple of things on this that we already know. If we have y equals 3x minus 4, a linear function has the form y equals mx plus b. So the slope is going to be the number that's in front of x, and then the y-intercept is this number represented by b. So what we'd have is the y-intercept is really going to be that 0.0, negative 4. Okay, so we're going to go ahead and we're going to sketch a graph without our calculator. Then we're going to do some work and formally represent the notation behind limits. So let's go ahead and plot out your y-intercept of negative 4. Okay, so we got a dot there. Okay, then we have a slope of 3. So if we have a slope of 3 over 1, with that being rise over run, then we know that what we're going to do is go up 1, 2, 3 from there over 1. And then again, 1, 2, 3 over 1 like that, and so forth. Okay, so it's up 3 over 1. Okay, like that. And then what I'm going to do is just sketch in that line, and then we'll kind of formally begin to talk about what we mean by a limit of a function, at least in terms of the definition that we're going to look at with our form here. Let me pause this. Technical difficulty. Okay, so we're going to go ahead and put this in the graphing calculator so we can do a little bit of quick number crunching on this. So let's erase whatever you have in there, and let's put in the line 3x minus 4. I'm going to do this in a standard window. Anytime you want to go to a standard window, just press zoom number 6, and then that'll graph that from negative 10 to 10 like that. Okay, so what we're looking at on this is we're going to now formally look at the notation of a limit. So we're going to look at the notation that says the limit as x approaches 2 of 3x minus 4. We're going to figure out what that is and talk about that idea. So what we're kind of interested in is we're interested in what's happening at this graph when x is 2. Okay, so x is equal to 2. At that point right there, that's what we're interested in. Every time I do that, it doesn't do what it's supposed to do. So I'm looking at that point right there, and I'm going to just kind of draw like a vertical line that goes through kind of like that. And what we're going to do is we're going to look at values as we close in on 2 from both sides. So we're going to do some tracing real quick on this. So I'm going to trace at 1.8 and just kind of record some things as we go. So that's 1.4. Then I'm going to go to 1.9. Oops. Okay, kind of close in on this, so that's going to be 1.7. Close in at 1.99, again getting a little bit closer to that value. So I go 1.99. I like that. That's going to be 1.97. Now I'm going to go a little closer. I'm going to go to 1.999. And that's going to be 1.997. And I'm going to trace at 2. And that's going to be 2. And I'm going to start here and kind of work myself backwards. So I'm going to trace at 2.2. Record that. I'm going to use red to represent that, so that's 2.6. I'm going to trace at 2.1 and record that as 2.3. I'm going to trace at 2.01, and that's going to be 2.03. And one more time, I'm going to trace at 2.001. And that closes us a little closer into 2.003. Okay, so the idea that what this is trying to show is as x is getting closer to 2, we're getting closer to 2 from the left-hand side and closer from the right-hand side, what's happening is the function values are getting closer to 2. So when we're looking at that limit, we're looking at what that function value is getting close to. So we would say that the value of the limit of the function 3x minus 4 as x approaches 2 would be equal to 2. Okay, that's kind of a informal way to help students begin to get the idea of what a limit is. Okay, and it's kind of like on that video I had you watch. If you did a half plus a fourth plus an eighth and so forth, like on Zeno's paradox, eventually you would get 1. Okay, and that's kind of a crazy idea to students at the beginning, is the fact that you could sum up an infinite number of fractions and get a finite answer. But that's how we resolve Zeno's paradox with calculus, with the idea of the limit. Okay, so now we're going to look at, we have a two-sided limit, just mainly getting used to the notation. It's going to look like x approaches a, so you've got just the basic arrow that goes like that. Then we have what we call a left-hand limit, which means we're going to approach only from the left-hand side. The notation on that is going to say x approaches a from the negative side. Then we have a right-hand limit, and the notational system we're going to use on that is x approaches a with a plus. That means we're approaching from the right-hand side, like that. Two-sided limit, you're closing in on both. So if you look at this diagram, the left-hand limit would be represented by these x values from the left of 2 closing in. The right hand would be these bigger numbers, bigger than 2 closing in on 2. Two-sided limit would be closing in on both sides at the same time. Okay, so next problem, we're going to do something very similar on this one. So I'm going to go ahead and, again, just make a plot on this. I'm not going to use the calculator except to fill out this table. Okay, so if we want to find an x-intercept of this particular quadratic, we just set the function equal to 0, and then we can solve this by factoring, or we can solve it by the square root property if we'd like. So we get x-intercepts at -2 and x equals +2. So I'm going to put a dot at 2, a dot at -2. We know that this thing is switching down 4, so if we want to find a y-intercept, what we do is we just we let x be 0, so we evaluate this function, we find g of 0, which is 0 squared minus 4, so that's going to be -4, so we're going to have our y-intercept down 4 like that. Now I'm just going to sketch in the parabola. Oh, what in the world did I just do? I didn't want that to go to Windows. God, this thing's crazy sometimes. Okay, and I don't know what caused it to do that. I pressed a button wrong or something. I did it again. God. Okay, let's try not to do that again. All right, so we got that. That's what the graph is. Then I'll turn off the internet because I don't even want to go there. All right, I'll let crap off of there. Okay, now we're going to take our calculator. We're going to do some limits, and it's going to get a little redundant doing all the tracing on this, but we're trying to establish an idea that's pretty important. So we're going to put in x squared minus 4, and we're going to graph that in a standard window. So I'm going to go zoom 6 to get a similar graph to what I have done by hand. Then I'm going to trace at different values. So I'm kind of interested, if you look down in my diagram here, I'm interested at the limit as it approaches -1. So I'm going to just kind of go to this value right here, and I'm going to put kind of a dashed line going through that point like that. And we're going to close in on -1. I'm going to highlight this, and then we're going to do some values closing in from the left like that. Let's go ahead and do that. So let's trace at -2, do this fairly quickly and just record this. So that's 0. Close in at -1.1. Okay, and that's going to give -2.79. Get a little closer. We're going to trace at -1.001. And that's getting to be, oops, I think I missed one of them. So that's going to be -2.997999. And I'm going to trace at whoops, not that. I want to trace at -1.01 is what I missed on here. So that's going to be -2.9799 like that. Let me zoom on that a little bit bigger so I can see this a little bit better. as to what I'm doing. Okay, so one thing you're going to notice on this, as x gets closer to -1 from the left-hand side, this value looks like it's getting closer and closer to -3, possibly. Okay, now I'm going to close in from the right-hand side and trace out these values here. So what I'm doing is I'm getting a little bit to the right of -1. So I'm going to trace at 0, and I'm going to record these values. Okay, so that is -4. Let's trace at -0.9. Okay, that's going to give -3.19. And let's trace at -0.99. Again, we're getting closer. So that's going to be about -3 and I think that is 0.199. And then let's go a little closer. Let's go -0.999. See, that's a number that's slightly to the right of -1. So that is giving about -3.001999. So it looks like they're approaching this same value. So notice if I trace at -3, that's going to be the point that I'm heading towards. I think I put the wrong thing in. So if I trace at -3, you're going to have, or not -3, I want to trace at -1. I got to pay attention here. Trace at -1, that's going to be -3. Okay, so that's what we end up getting. The calculator kind of shows you what the value of this limit is. So the left-hand limit is, we're going from the left-hand side, kind of like this. So if I was to go through and just kind of trace out on this graph from the left-hand side, I would be getting closer to that y value of -3. So that left-hand limit's -3. The right-hand limit, I'm going from the right side on this, getting closer and closer and closer to x equals -1. That's approaching -3. And then the two-sided limit's going to be the same thing. So what you're doing on this primarily is this. I'm going to do something with my calculator. I'm just going to bring this graph over here so you can see a couple of things here that I'm doing. The first idea on this is when we're doing a left-hand limit, I want to use this graphing calculator icon because it'll show this pretty clearly. So what I'm doing on a left-hand limit is basically I'm doing this. On a left-hand limit, I'm interested at x equals -1. So I'm just basically tracing the left side of that and getting closer to that y value is getting closer to -3. And then if I want to trace in from the right side, I'll use this orange highlighter to show that. I'm getting closer and closer and closer to -1. I'm also going closer to -3. So the idea is when we're doing a limit as x goes to -1, we're interested in what that function value is getting closer to. And that function value is getting closer to -3. So that's kind of an informal demonstration of what a limit is trying to show you. Okay, let's do a piecewise function. Now let's do a graph on it. And what we're going to end up having on this, I'm going to actually do two tables of values. When I do piecewise functions, I think a lot of times students do a little bit better on piecewise functions if they go through and just make a couple of tables of values. So that's what I'm going to do over at the side here, is make two tables of values. And let's start the first one just by doing x. And the first piece is the line 2x plus 3. So we're going to crunch out some values for y equals 2x plus 3. And we're only using numbers that are smaller than 1. Now I'm going to go ahead and use 1, but I've got a bubble there because that's less than. It's not greater than, so I'm going to have that. Then I'm going to choose a couple of values that are smaller than 1. Keep it kind of simple, and let's do like -1 like that. Okay, so I'm going to plug this in. Do 2 times 1 plus 3. 2 times 0 plus 3. 2 times -1 plus 3, and so forth. So this is 2 plus 3, so that's 5. This is 0 plus 3, so that's 0. This is -2 plus 3, so that's equal to 1. So I'm going to go ahead and go to my graph, and I'm going to plot some points on this. So at 1, 5, I'm going to put a open bubble there. Then 0, 3, I'm going to put a dot there. Come on, doesn't let me put dots on here. Makes me so mad. 0, 3. Come on, just let me put a damn dot there. There we go. Right, negative 1, 1. So I'm going left 1 and up 1 like that. And then I'm going to do a line on that and just sketch that out as the first piece of our piecewise function as a line. Okay, so going from that open bubble through those points, that would be our first piece like that. Okay, right, now what I'm going to do is I'm going to do the second table of values with the second piece. Just kind of doing the same idea here. And this time we're going to have x and we're going to have y equals, the second piecewise function is going to be 2x minus 3 on a different interval. So we're going to sketch out 2x minus 3. Again, we're looking at x is greater than or equal to 1. So since we're equal to 1, we're going to have a solid dot there. Then we're just going to pick a couple of points that are bigger than 1. So I'm going to do 2 times 1 minus 3, which is negative 1. 2 times 2 minus 3 is 1. 2 times 3 minus 3 is going to be 3, like that. Okay, now I'm going to go ahead and plot those points. So I've got 1, negative 1 down here, which is a solid dot. Then I've got 2, 1. And I've got 3, 3. Like that. I don't think I quite did that right. So I've got a solid dot at 1, negative 1. Okay, so every time I try to do a dot, it won't let me. And then 2, 1, and then 3, 3, like that. Okay, then I'm going to go ahead and sketch that in just with a different color to represent these are the two pieces that we have then. Okay, so that's the second piece. So that's a graph of your piecewise function. Now what we're interested in is we're interested in the limit as x approaches 1. So what I'm going to do on this is that's where we have a break in the graph. So I'm going to go through on here and just kind of take a dashed line going through x equals 1, and we're going to do a left-hand and a right-hand limit on this then. Okay, we're going to use the calculator to assist us with this a little bit on this section. This is a good way to do an informal demonstration of what limits are to calc students. So what I'm going to do is I'm going to put in, first of all, I'm going to put in 2x plus 3. Okay, like that. And 2x plus 3 is this function on the left. So I'm just going to kind of make a note that that's 2x plus 3. That's what the red piece is. Then I'm going to trace in values closing in from the left, getting closer to 1. So I'm going to go ahead and graph this in a standard window, which is a line. And then I'm going to close in at certain values in my table. So let's trace at 0.9. So that's going to give about 4.8. Let's trace at 0.99, a little closer to 1. That closes in at 4.98. Then we're going to close in a little closer, 0.99. See, that just gets closer to 1. So that means the y value is getting closer to something. So if you look at this, the y value looks like it's approaching 5. Okay, that's what we're going to see when we do our limit here in a minute. It looks like that's approaching 5. Okay, all right. So that left-hand limit, which is represented by this one, is going to be approaching a value of 5. You can tell by the graph on that, that's getting closer to 5. Okay, now let's put in the calculator. Let's put in the piece on the right, y equals 2x minus 3. So I'm going to erase this, and I'm going to put in 2x minus 3. Graph that again in a standard window. And I'm going to trace out some values on this going from the right of 1, kind of closing in like that. So let's start at 1.1 and trace that. Okay, you got to graph first. So got the graph, type trace, type in 1.1, and that looks like that's going to be about negative 0.8. Let's trace a little closer to the right of 1. Let's use 1.01. So that's going to be about negative 0.98. And let's go one more time, a little closer. Let's go trace in at 1.001. and that's going to be about negative 0.998. So it looks like as you're going closer on this, it looks like that is approaching approximately negative 1. That value is getting pretty close to negative 1. So that right-hand limit, represented by part C, is going to be closing in at negative 1 like that. Okay, so that's the idea. And then the two-sided limits go into two different places. So that we're going to say that that does not exist. We use the abbreviation DNE just as an abbreviation for does not exist. It doesn't go to the same place. So one thing that you want to kind of do on here, you can kind of trace this out. The left-hand limit, I'm going to the left of this, and I'm getting closer and closer to a function value of 5. On the right-hand limit, I start over at the right, and I close in to x equals 1 from the right. I'm getting closer to that y value of negative 1. And then since the left and right-hand limit don't go to the same place, that's why I conclude that that does not exist. Okay. Now I'm going to go ahead and review a piecewise function and how you put this in a graphing calculator. Kind of a nice thing to know. You actually go like this. You go y equals. You put in the first function, which is 2x, like this. Let me close this and open it again. So we're going to put in 2x plus 3, close parentheses, use the division symbol, left parenthesis, put in x. Now go to your test command. So you go second math to get that to open up. Now we're going to say less than. So we put less than, just press enter, and then put 1. And see, that will graph just that piece. Then we go to the next part of the piecewise function, which is 2x minus 3, close parentheses, use the division symbol, then use a new parenthesis, put an x, and now put in greater than or equal to 1. So we go second math to get the test button to come up. Then we're going to put in greater than or equal to 1, close the parentheses. Okay, now if I do a window, just a standard window, zoom 6, okay, it'll graph the way the piecewise function is supposed to look. So I'm going to just kind of show you something on this. I want to put this on here and just show you a couple of things on this, what's happening. So the idea with this limit is we're interested in the limit as x approaches 1. So we're kind of looking at a barrier where x equals 1. And the idea on this is the left-hand limit approaches a different value than the right-hand limit, like that. Okay, so this would be your right-hand limit there. This would be your left-hand limit here. So they approach different values. So basically you're looking at function values. The left-hand limit is heading towards 5. The right-hand limit is heading towards negative 1. Therefore, the two-sided limit does not exist. So that's the idea. Okay, now moving on to the next thing, we're going to look at some a couple of basic theorems. Okay, so using the last problem as an example, what this problem is saying is if the left-hand limit, this represents a left-hand limit, that goes to L, and then this is a right-hand limit, that also goes to L, then we would make the conclusion that the two-sided limit is going to approach that same value. Okay, so I think I might have a misprint on this right here. So this is saying if the limit from the left exists, the limit from the right exists, and they're both the same, then the two-sided limit is also that. So I think this right here should be saying limit as x approaches a of f of x, that's also going to be L. So if the left-hand limit, which is represented by this, is the same as the right-hand limit, then the two-sided is also going to be the same. So that's a theorem that we have. If they go to different values, if the right and left hand go to different values, then the two-sided limit doesn't exist. So that's what that is. Okay, so let's, on this example 3, let's go ahead and graph this piecewise function. Without a calculator, first thing we're going to do is we're going to do this piece, kind of getting that put together. So we're going to be looking at y equals square root of x, and we're going to be looking at values greater than or equal to 0. So I'm going to start with 0, and I know I've got a solid bubble because it's got the equality there, then I'm going to take some numbers that are bigger than 0 that I know square roots of. So I'm going to use those numbers right there just to simplify this. So I'm going to do square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and finally the square root of 9, I'm kind of thinking ahead there, the square root of 9 is going to be 3. Okay, so we got those values, so I'm going to go ahead and plot this in red down in my graph right here. Okay, so I've got a solid dot on 0, 0. I got 1, 1. I got 4, 2. And all the way out to 9, 3. Like that. So that kind of gives the shape that we expect to get with a square root. So I'm going to label that y equals square root of x. And see, that is on the interval x greater than or equal to 0. Okay, then I'm going to do the second piece, which is an absolute value function. And what we're going to do on this is we're going to be less than 0. So basically what's going to happen here, since that doesn't have equality, that's going to be open right there. And then you're going to take numbers that are smaller than 0, like -1, -2, -3, and so forth. So you're doing the absolute value of each of these x values. So that's 0. Absolute value of -1 is 1. Absolute value of -2 is 2. Absolute value of -3 is 3. Okay, then we're going to plot these. I'll use a different color. So we got 0, 0, so that's the same point. We have -1, 1, -2, 2, -3, 3, so that is going to give us a line. So I'm going to go ahead and just graph out the line. These two things do connect at the same point, so that means we aren't going to have a open bubble there. It's going to be closed in. Okay, so that's what that graph looks like. So what we're going to do on this is we're going to do a couple of limits. Okay, part A is going to be your right-hand limit because it's got the plus sign. This is going to be a left-hand limit. It's got the negative, and then this one is going to be the two-sided limit like that. Okay, so the idea with this is if you kind of just imagine in your mind going through and just kind of thinking of, okay, I'm interested at x equals 0. So I'm just sort of drawing a little vertical line through x equals 0. And if I'm going to go through and close in on this a little bit, I'm going to use a little bit different size highlighter on this now. Okay, so if I go from the left side, the left-hand limit, I'm just basically closing in from the left. And what I'm doing is I'm getting closer to that y value of 0. So that means that left-hand limit is going to be 0. Okay. The right-hand limit, again, I'm going to close in mostly from the left-hand side or from the right-hand side. So I'm going to get on the square root and I'm going to close in that way. And again, I'm getting close to 0. So that right-hand limit is also going to go to 0. So by the theorem that's on the top of the page, since the left and right hand both go the same place, we conclude that the two-sided limit also goes into 0. Okay, this one would be put in your graphing calculator like this. You would put in square root of x, division symbol, and then x greater than or equal to 0. And then you would have to go ABS, I'll show you where that is, of x, and then division symbol, x less than 0. So let me go ahead and get my calculator out and show you that, just kind of so you know the ABS and where that is. So I'm going to go to y equals, I'm going to clear off these two things and put it in like this. Okay, so in y1, I'm going to put in a parenthesis, I'm going to put in square root of x. Go like that, don't want to do that. Okay, I always mess up on that nested feature on this. I'm not used to that. So again, let's go left parenthesis, square root of x. Now I want to get out of that, so I do that. Now I need to go back up here to wherever I was. I need to go up there. I need to get past that, put a parenthesis, division symbol, and then the left parenthesis and the condition. So I go x, second, math, to get the greater than symbol, greater than or equal to symbol to come up. So I do that and close the parentheses. So that's going to do that. I've got to put the 0 in though. Okay, like that. So that's good. Now ABS is found under math, and you might want to make a note on that. So if I press math, number, that's where ABS is. So again, that is math, number, okay. Option 1, ABS comes out, and then we're just going to put an X in there, get out of the symbol, do division, and then do X less than 0. So we go X, second math to get the test command to come up. And then we want to do less than 0. And then that should graph that in a standard window. So if I go zoom 6, that's the square root, that's the line. So that's the graph that we get on this then, okay? So a graphing calculator is kind of a nice thing to do some piecewise functions in. Now again, you want to be sure that you understand how to do it both with and without a calculator. So the left-hand limit would be represented by that. Right-hand limit would be represented by that. They're both going to the same function value. Okay, moving on to the next example, we're going to go ahead and I'm going to pause on this one and let everybody go ahead and do this problem themselves, okay? Okay, so let's go ahead and get our table of values put together and make sure you did that right. So the first piece is going to be the line, x plus 2, and we're going to use values that are greater than 2. So I'm going to start with 2, open bubble, make a marker to yourself, and then take numbers bigger than 2, 3, 4, 5, just to get enough. You know that's a line, so we're going to do replace x with the x value in our table. So we'd have 2 plus 2 is 4, 3 plus 2 is 5, 4 plus 2 is 6, and 5 plus 2 is 7. So that'll give that. So let's go ahead and I'll choose a color like red and we'll do that. So we have a point 2,4 where I have an open bubble, and I've got 3, 5, and I've got 4, 6, and 5, 7. So I think I got all my points correct on that. And I'll just draw out a line on that, going from the open bubble, going forever like that. And I'm going to label that as y equals x plus 2. That's going to be x greater than 2. Okay, then I'm going to do the second piece, which is the quadratic. So I'm going to do that in a different color. So let's see, we're going to start with 2. We are solid at 2 because of the equality. So that's a solid dot. Then we're going to pick numbers smaller than 2. Let's pick like 1, 0, -1, -2. And crunch them out in the quadratic. So we've got 2 squared minus 2. 4 minus 2 is 2. 1 squared minus 2 is -1. 0 squared minus 2 is -2. -1 squared is 1 minus 2, so that's -1. And -2 squared minus 2 is 4 minus 2, so that's 2. So let's plot those points. So we have a point 2, 2. That is solid. Okay, and I got 1, -1, 0, -2, -1, -1, and -2, 2. And then we can go ahead and sketch in that quadratic like that. Okay, so that's how that goes. Now we're going to do left and right hand limits on this then. So we're interested in, and I kind of wonder on this. I'm kind of thinking that maybe I meant for these to be 2s. I think that's what I'm going to go ahead and have you do on that. That's obviously a typo. It doesn't matter. I mean, you can still do the problem this way, but my intention was to have you do the limit as x approaches 2 from the right side of g of x, the function's g of x, so I didn't type that right. And then this one, we're going to look at the limit as x approaches 2 from the left-hand side of g of x. And then part C, I was interested in the limit as x approaches 2. That's a two-sided limit of g of x like that. Okay, so let's go ahead and just look at these things real quick. Okay, so let's start with the right-hand limit. Okay, so I'm going to take a Oh, like a color, just kind of a real small, let's do like pink or something like that, okay? The right-hand limit, what you're doing on that is you're basically just closing in from the right-hand side like this, okay? That's the right-hand limit. We're going to get to the right of x equals 2. Now, first of all, what we're doing on this one again is kind of looking at a boundary. So I'm going to just kind of visualize a vertical line going through x equals 2. So the left-hand limit, what I'm going to do on this left-hand limit here is just get on the right side and kind of close in. So I'm closing in. Now, what function value am I getting closer to? You're getting closer and closer to a y value of 4. So that means the right-hand limit is going to have 4 is going to be the answer. Now, the left-hand limit, I want to get to the left of x equals 2, get on the quadratic, and kind of close in this way. So as I get closer and closer to that boundary, I'm getting closer and closer to a y value of 2. Okay, now this is not going to exist because the left and right-hand limit are approaching different values. So that's how that would go. Okay, now I'm not going to do this one on the calculator, but the idea with this would be you would put this in like this, x plus 2, x greater than 2. That would put the linear in, and then the quadratic you'd put in x squared minus 2, division, and then x less than or equal to 2. And then you would get a similar graph. Okay, so let's move on. And to kind of finish this up, we're just going to look at some general diagrams and answer some questions about limits on these then. Okay, so let's start with these first limits are looking at x approaches negative 2. This one is a left-hand limit. Part B is a right-hand limit. And part C is a two-sided limit. So you want to be sure that you're solid on that. So since we're interested at negative 2, what I like to do is I like to go through and just kind of go to x equals negative 2 and draw a dashed line to kind of help me see what's going on in the problem. Okay, so we're going to do a left-hand limit. So that just means get to the left of the boundary and then kind of close in on it like that. So that's getting close to a y value of 3. So that left-hand limit is going to approach 3. Okay, the right-hand limit, you want to get a little bit to the right of the dashed line, not way over here, but just over in here somewhere, and start closing in. So as we go from the right, we're going to the same place. We're closing in towards a y value of 3. Now remember, it's y values that you're looking to. So as you get closer from the right, you're getting closer to that y value of 3. The two-sided limit is going to be the same because those two things, the left and right-hand limit, go to the same value. So that'll take care of that. Now we're going to move on to 1. So again, I'm going to draw a dashed line going through x equals 1. And we have a break in the graph going like that. And I'm going to erase what I did over here so I can see this a little bit better. So now we move over here, and the left-hand limit. So what we have is we have a left-hand limit there, we have a right-hand limit, then we have the two-sided is kind of what I'm looking at in each of these cases. So the left-hand limit, get to the left of that boundary, kind of close in like this. Now one thing I can do to represent this a little better is kind of go like this. So I'm just kind of closing in. Now what y value am I getting close to? I'm never going to hit that y value of 1 because there's an open bubble there, but I'm getting close to 1, and that's all that matters. Okay, I'm getting closer and closer to a y value of 1. Now if I go from the right-hand side, I'm going to come over here, and I'm just going to kind of close in like this. Okay, where am I getting close to? I'm getting close to a y value of negative 1. So that means that the two-sided limit would not exist because we're going to different places. The left-hand limit's heading towards a y value of 1. Right-hand limit's going to negative 1. Therefore, two-sided limit does not exist. Okay. All right. And then the next one, we're going to look just at 3. So just for something a little bit different here, I'm going to erase that. Okay. So if I go to 3, I'm going to put a little boundary through x equals 3. This is a two-sided. Okay, then what's happening is this. Okay, I need to get, if I'm going a little bit to the left of 3 and closing in on it, I'm getting closer to a y value of 0. And if I close in from the right-hand side, so I'm on the right side of that boundary, I'm going to the same place. So you're basically heading towards a y value of 0. So the two-sided limit does exist in that case. Then the last thing I want to do is look at 4. I do have an asymptote already drawn out on that. So we'll kind of look at the way this goes then. So this is a left-hand limit. This is a right-hand limit. And again, this is a two-sided limit. So we want to do that. So here's the vertical asymptote, x equals 4. And I'm going to go a little bit to the left of it. So as I get closer and closer to that asymptote, the y value is kind of getting out of control. That's going towards positive infinity. So we say that that limit is going to infinity. Okay, if we do the right-hand limit, I'm going to go like this. I'm going to close in from the right. Same thing. The closer I get to 4, the higher the y value goes. So it's also going to positive infinity. And since they go to the same place, we would make the same conclusion about the two-sided limit like that. So limits can take on a value of infinity or negative infinity. Okay, moving to the next page here. So this is next thing. I've got a graph here that I want to look at different values on. Okay, so as we go through these, the first one is a two-sided limit. So we're interested as x goes to 6. So x equals 6, I'm going to just kind of visualize a dashed line going through 6. And I'm going to do on a two-sided limit, I'm going to go from the left of it and then to the right of it. So the left-hand limit as x approaches 6 seems to be heading towards that y value of 2. So this one is a left-hand limit. That's going to 2. Right-hand limit, if we get to the right of 6 on this function and close in, get closer and closer and closer, but not quite to 6, like at 6.000001, looks like we're heading towards a y value of 5. So they're going to different places. That means the two-sided limit, like we've learned, would not exist. Okay. Now we're going to go to negative 8. So at negative 8, I'm going to draw a dashed line through negative 8 to represent that. Now we have a bubble there, but we have a solid there. That's where the function is. One note I want to make on this, if I ask you for f of negative 8, f of negative 8 is negative 3, okay, because you have a point, negative 8, negative 3 on your graph. Okay, that just means the function's defined there. It's not defined at the bubble. Okay, so let's start with the left-hand limit here. So let's get a little bit to the left of negative 8 and just kind of see where we're closing in. So as we're getting closer to negative 8 from the left, we're getting close to a y value of negative 6. It doesn't matter there's a bubble. It's just if we're barely to the left of negative 8, we're getting close to that y value of negative 6. Okay, then we have the right-hand limit. So I'll take another color for that. We're going to get to the right of negative 8 and close in. So I'm closing in, closing in, closing in. I'm going to the same place. I'm heading towards a y value of negative 6. So since the left and right-hand limit go to the same place, the two-sided limit is also going to approach negative 6. So that's how that goes. Okay, now we're going to turn our focus now to negative 2. Okay, so on this one, I'm going to just kind of draw a boundary at negative 2. Okay, so we're just interested in just negative 2, and we're going to do a left hand and right hand limit on this. Okay, so let's start with the left hand limit as x goes to negative 2. Get a little bit to the left and close in. Remember, it's what function value, what y value we're getting close to. So we're getting close to that y value of 3. Okay, now I want to go, and I don't know what in the world I did. I don't care about going to Windows 10. I don't know why it's doing that. It's causing that button to press somehow. Okay, so now I want to go to right-hand limit as x goes to negative 2. So if you look at this, if we're closing into an x value -2, we're getting out of control, so it looks like that is going to positive infinity. Okay, so again, the two-sided limit's not going to exist because those two things are going in different places. Okay, and then to finish up, we'll look at what's going on in this graph at, say, at 10. Okay, so I'm going to draw kind of a dashed line going through 10. Okay, and then we're going to do the left and right hand limit. So the left hand limit, let's get to the left and close in. Okay, so if we're going from the left hand side until we get to 10, we're closing in on a y value of 0. And then if we do the right hand limit, I'm going to get to the right of that dashed line on the function. And see, we're going to the same place. We're getting close to a function value of 0. So that means the two-sided limit would also be equal to 0. Okay, so that kind of gives you a little bit of every scenario that you see on graphs, and you do this frequently on exams, as you want to be able to interpret limits correctly. Okay, last page on the handout. I'm going to show you kind of what happens on these. These are kind of interesting graphs. I'm going to use my graphing calculator to try to demonstrate this the best I can. So I'm going to put in, let me erase everything that I have here, and I'll see if I can get my graphing calculator to work okay for this. So I'm going to look at this function sine of 1 over x. And we're just going to look at what happens close to 0. So I'm going to put in sine 1 over x. And what I'm going to do on this one, for my window, I'm just going to go -1 to 1 because I'm kind of interested in this limit, see, as x goes to 0. So I'm going to get a little bit to the left and a little bit to the right of 0. And let's see, I think I'm going to do maybe something like -3 to 3 and just kind of start that way and see what we get. So I'm going to graph that. You kind of get a crazy sine wave kind of going on like that. In fact, I'm going to change my window on the y to -2 to 2 so you can see this a little bit better. So I got -2 to 2, and I'm going to now type graph, so I kind of get this. Okay, and I'm going to slide that over there. Now what I'm going to do is I'm going to zoom in on this. So I'm going to do this thing called zoom box, which I kind of like. I'm going to do zoom option 1 box, and then I'm going to draw a box around this. It's kind of hard to see my cursor, but I'm just getting a little bit to the left in there, and I'm going to press enter. Then I'm going to press my right cursor, because basically what I'm trying to do is draw a box around this. And then I'm going to go down, getting below the y-axis till I get into some of the negatives. So I'm drawing a box around that. If you can kind of see on here, I press enter, and it's going to zoom on that, and it just kind of looks the same, doesn't it? It's almost like complete chaos going there. So if I continued to zoom in on this over and over and over again, if I did a zoom box again and just kept zooming in, you can also just go zoom in, option 2, and zoom in on it. I just keep zooming in, and it looks like it keeps doing the same thing. Looks like total chaos going there. And I could zoom again and again and again and again and again, and I just can't really make any conclusion about this graph. It's just very chaotic. So what you would find on this is this limit would not exist. And the reason is because x does not approach any specific value. So it's not doing any specific number. That's the idea. That's a little bit different. Now, if you look at this next one here, what you have on this one's a little bit different situation. So if I go back and if I insert and put in an x and graph out x sine of 1 over x, and I'm going to do that, adjust that back to -1 to 1, and take my y from, I'm going to take my y maybe from, let's go -0.5 to 0.5, kind of scaling in like that. And if I graph that, it looks a little different. You got a sine wave kind of going like that. So it's a little bit different idea. Okay, I think I got the x in there okay. So I got x sine 1 over x. And let me double check and make sure I got everything right on here. That should be okay. Now I'm going to go ahead and change my y just to -1 to 1. And make sure I got everything in there correctly. And graph this one out. Now this one appears to be going somewhere. So if I was to go through and just zoom in, so I'm going to just press, you can just do this zoom in, option number 2 if you want to, and it's going to zoom in on that little part right there. So notice that it looks like it's going to 0. And if I zoom in again, option 2 again, then it starts, that's kind of what it kind of starts looking like this graph over here. So the idea is this one is going to approach a specific value on this. So this one is going to go to 0. Okay, so we would conclude on this one that the limit as x approaches 0 of x sine 1 over x would approach 0, because you can pretty well tell on this that it's closing in on that y value of 0. So that's it. So those are a couple of other interesting kind of graphs that you also will come across. Very interesting. Okay, so that will wrap up everything we need to know on this section then.